Kenapa ni? Atikah. Some of you have problem to join the class, is it? Oh, why? Atikah cannot join. Not sure. Are we still waiting? Shall we start or shall we still wait? I have to finish it by 12:30. Macam ada kawan awak yang tak boleh masuk ni. Okay, I think saya I will start now. Let me change the sharing slide. Stop sharing and we share another one. Masih. I think Yusri as usual akan record kan. Saya pun akan record juga. Yang mana yang boleh. Where is my slide? Here. Can you see the chapter 10 PDF now on the screen? Boleh? Hmm? Mana dia tadi? We have 43 participants now. Right. You can ask questions if you require. So can I have your attention now? Are we ready? Class? Can somebody reply? We have what? We will Jason. Okay, Israel. Okay, so Assalamualaikum warahmatullahi wabarakatuh and good morning. So today we will continue with chapter 10 from your module, which is on FSM or finite state machine synthesis. Okay, is my voice clear? Right, let me start record. Okay, so this is a backup. Right. So, so this is chapter 10. What is it? Let's see. Okay, so the content of this chapter basically is design process. And then we go for examples of design process on how to design a single mode counters, and then how to design a multi-mode counters, and then we do sequence detectors. So for the sequence detectors, actually you have experience with it by doing your milestone 4. So focus for design process today, we're going to only use the um what is it, the binary encoding or gray coding. Okay. Okay, so design process, as we mentioned before, there are going to be 1, 2, 3, 4, 5, 6. Basically, first is again from the conceptualize or the problem statement. So you have to understand the statement of the specification. So basically, from the statement, you should be able to identify how many flip-flops, uh, that means the how many states, how many inputs, what are the inputs and the outputs. So the best way to do it is uh, by representing the statement into top level block diagram. Okay. Some of your friend ada issue internet tak boleh support apa kita record. So the second one you capture, translate the problem into state diagram. So that is the second process. Okay. Then you determine the number of state required, input, output, and state transition. Right. And then encode the state, assign a unique binary number to each state. So this is the part that you have to decide, either to use binary encoding or gray coding, Johnson coding, or one hot coding. And then create the state table. So if you use one hot, you don't have to create the state table. And you extract the equation. So normally from the state table, you have to I got distracted by the message from your friend. You have to normally you do K-map to get the equations. So you have to remember, if you forgot about K-map, you have to remember. You have to recall and make sure you don't make mistake on the K-map. And then of course you can draw, you can start implement the FSM. I don't expect for the implementation for you to draw very much, but I prefer for you to start using quarters tool. Okay, right. So that are the steps. So definitions. So now let's go for counters. Now counters is special finite system such that starts from a particular state. Normally it starts from the number, for example, from 0, and then it going through fixed sequence of states, and then return to the initial state, and it repeats indefinitely. For example, if you have like digital watch, your number, the hour number, it goes from 1, 2, 3, 4, 5 until 11, 12, and then it go back to 1. So it go, that is why we said counter is actually clock, counter. So it goes from that. So like our watch, the hour is from 1 to 12 and then repeat. However, like for the second counter, it goes from 0 until 59 and go back to 0. I think the 60 will not be displayed. Once you go to 60, it go back to 0. So these are the repeating sequence. So that is examples of counter. And most counter, but not all, but it's called MED-VDIF state machines. It's a new name, but don't worry about that. What it means is that this FSM doesn't have the output, a special output, or no special external output. What happened is that the register output itself is the output. I mean the number that represent the coming out from, or the state itself from the counter, from the register or from the flip-flop is the output itself. So you may have single mode counter. So single mode, normally the input is just clock. Sometimes we call binary counters is the counters that counting the clock pulses. It's just that when you reach the maximum, it will return back to 0 or to the original numbers. You can count up, you can count down. You may also have multi-mode counters. For example, you have external input up down, for example. If the up is activate, it will count from 0 to some numbers. And if you say down, activate, it will count the other way around. Yeah. So that is a multi-board counter. So for multi-board, you not only you have the clock signal, but you also have normally external control signal, we call it. Now, this is an example of simple binary counter. So, n binary, if you have 2-bit counter, so now you can also have the counter sequence from 0, 1, 2, 3, 0. So that means this counter start from 0, it has 4 state, and it will repeat to 0. Yeah? So the round figures here, 0, 0, 0, 1, 1, 0, 1, 1. Now the state is already defined by the counter sequence or the counter number that you want it to appear. Eh? So you don't have, uh, you don't, you don't, you don't really categorize counter as milli or more, because there is no output in the state, because the state itself is the output. So therefore, once you have again, the statement, if it's a 2-bit counter, the maximum we can count from 0 to 3. So this is just a binary count. And what you do next is you do present state, next state. You don't have the input, you don't have the output. And this next state is your output. So if you look at it from 0, 0, so if your present state is 0, 0, next it will go to 0, 1. If you start from 0, 1, next 1, 0. And then if you go from 1, 0, next we 1, 1. And once you are in the third state, so from 1, 1, it will go back to 0, 0. And recall that our decision is we use D flip-flop only. So for D flip-flop, by right, when you design, you have present state, you have next state, and the third thing is you have, actually you should have here D flip-flop or the flip-flop input. But because you use D flip-flop, this one will be your sorry. This one will be the default is always the pad. Yeah. This is D1 and this is D0. Next state is actually also the D flip-flop input. Okay. Now, what next is from the D flip-flop? You see, Q1 plus is equal to Q. If you look at this one, Q1 plus is simply 0, 1, 1, 0. So you don't really need to do K-map because it's very simple, only 2-bit. So you know, you see 0, 1, and 1, 0, that will trigger the Q1 plus. And Q1 plus is basically D1 here. Basically, it's D1. Okay. And okay. And similarly, okay, for Q0 plus, this one is actually for D0. Eh? This is actually for D1. Because remember, for D flip-flop, this is actually D1. This is actually D0. That's why enough to go until next state. And the output, the status of the state, which is the next state here, the Q1 and Q0 is actually your output. Eh? This is actually your output. So that is easier. Counter would be the easiest FSM indirectly. You don't have, because this is a straightforward counter, right? You may also have different type of counter. I think next one. This one is if you have arbitrary sequence, meaning sequence that can just be any random sequence. For example, if we want to stick to n of 2 or uh, number of state less than 2 to the power of 2, which is 4 state, can be, for example, this is also modulus 3, but this modulus 3, for you can have 0, 3, 1, 2, you can have 1, 3, 2, 0, you can 0, 1, 3, 0. This is what it means by arbitrary. Arbitrary mean any whatever sequence that you like. Okay, and the sequence here actually it may also reflect, for example, in a factory, the first sequence could be the first process that you have to do. So the maybe this one will trigger a certain type of sensor, for example. Once finish this step, it will go to the next step and then go to the next step and repeat. So this is also a counter because it repeat the process. When it repeat a process, it is called, this is the definition of a counter, right? Now, if you have the arbitrary sequence, now, although your sequence just now is 0, 1, 3, but when you do your K map or your state table, this is called state table. This is called state table. So state table is nothing but alternative representation of the state diagram. Whatever you have from the state diagram is here. So if you remember just now, after, if your present value, now, the sequence for your present state, keep in binary. Okay? Do not follow the sequence given in the state diagram. Okay? For the present state. But the next state, then you follow the state diagram. If, for example, in the state diagram given, after 0, 0, it go to 0, 1. So you follow the state diagram. After 0, 1, it jump to 1, 1. Go to 1, 1. After 1, 0, it's not defined. So something that is not defined, you put XX, means undefined or don't care. After 1, 1 is 0, 0. So you come up with the next state, and therefore, again, you can come up with Q1 plus. Q1 plus, actually, you can, if you do K-map or you have this one, 1x 0, 1, 1, 0, this is actually what? Is it right? Q1 bar? Oh yeah, it takes this pattern. Q1 bar, Q naught. Okay? Whereas for Q naught plus is equal to the round circle of this one. So that one is actually Q1 bar, Q naught is cancelled out. So just Q1 bar. And therefore you complete. So when you complete, whenever you have two state, obviously you have 2D flip-flop. And then clock is a must. So by right, these are the first thing that you do, right? And then you label Q1 and Q naught. And because this circuit is very simple, you can show the feedback. It's okay to show the feedback. But when you do quarters for a bigger circuit, let's say you do more than 2 flip-flop, perhaps rather than making this wire going around like this, you label, once you have the label Q1, you just put another inverter to get the Q1 bar. So here only label. You just use label. Okay. So arbitrary input follow the binary sequence, but the output here follow the state table. Okay. Next. Now you can also have multi-mode counter. So as I mentioned before, multi-mode is a counter whose counting sequence depend not only on the clock but also some control signal. You may have count out counter and count down, or gray binary or gray sequence, increment of 1 or -2, blah blah blah. Yeah. So this one like two options lah. This is if you have one signal control, you can have two function, up, down, binary, gray, or this one and this one. Yeah. So let's see what's the example that we have here. This is a up-down counter. So that means if you notice, as long as your signal is 1, here 1, 1, right? 1, 1, 1. It goes from, this is what? Count up or count down. If 1, it will do count up. 0, 1, 2, 3, 4, 5, 6, 7. However, if your input is 0, It goes from 7 to 6, 6 to 5, 5 to 4, and so on. But this is still a counter because it repeats. The process is repeating in a closed loop. Yeah? So this is the up-down counter. So therefore, uh, if you were to implement, again, you have input. So you can define the input as, in this case, use U. But perhaps the best symbol for the input is actually maybe up D, UD. But just now up is 1, so down bar. Yeah? So for example, you have U, D, bar. So that means this is one input. If if the input is high, it will up count. If it's 0, down count. You can do it this way. For example, this is your present state. If your input is 0, let me remove this big annotation, and let's do a new annotation. Let me try to look for my smaller pen. The pen is irritating a little bit. Okay. It doesn't want to give me a smaller pen. Here. Right. So now again, if you recall, if your up is 1, it will count up. So that means from 0 go to 0, it will go in circle going back to 7. If it's 1, it go to, sorry, no, we're not referring to this one. 1, okay, 0, this is countdown. From, again, if it's 0, but if it's 1, it count up. 0, 1. If it's 1, 1. From 1, if it's 0, count down, so 1 going to 0, and so on. Let's say, for example, 6. If your present value is 6, if it's 0, if your input signal is 0, it will count down. So 6 will count down to 5. However, if your input is 1, that means from the present state of 6, it will go to 7. That's how you fill up. You may also, actually, if you want to be comfortable, you can also put the input over here. If you put input here, let's say U here, now that one will be nice, because if you have this one, as long as your input is 0, it will do the count up. So the whole thing here, if you do the input here, it will count up. If the input is 1, then it will count down, right? So that means you put input here or input here, doesn't matter, as long as they are there in the state table. Yeah, and you can come up with the state next state. You may also have a situation whereby you have the output. For example, the design is that output equal to 1 when the present state is 5 or above. So if that is the cases, the output always refer to the present. So that means, let's say, output for greater than, greater than 5. Greater than 5. So that means greater than 5 for 5 here. This is 5. So here you have output of 1, and all here is 1. You can have it also that way. Yeah, you may have output because that means maybe you want an indicator or a light to turn on or something, right? To say something. When you reach certain numbers. Okay, also possible. Right. So then after that, in this case, this equation, I think this equation is not, this one obviously, you have to do K-map. Yeah, you will do K-map for Q2, Q1, and Q0. So once you do the K-map, which is skipped here, not showed here, you will come out with this equation. Okay? You will come up with Q2 plus, Q1 plus, and Q0 plus. And remember, we use D flip-flop. So D flip-flop meanings This is your D2 input, this is your D1 input, and this is your D0. Okay? So this is your D0 input. So this is your output, basically the Q state. And so several ways to realize the design. You can use the simple logic gates. You can use marks, you can use decoder, you can use ROM. That means you can use all this for the next state equation, right? But how many flip-flop you use? Because you have three Q's three state. Sorry, not three state. You say three, the encoding. The encoding is 3 bits, right? Obviously, meaning you use three flip-flop. Three flip-flop. Three flip-flop. Okay? So it depends on this how many bits. And this one is just for the next state equation. If you use marks, decoder, or ROM, then you don't have to get this equation. For ROM, for example, you just use a lookup table. For decoder, straightforward. For marks, you're going to use 3 marks, right? Because one for Q2, one for Q1, and one for Q0. And behavior Verilog is easier, but this is not in our scope. Okay? Right. Any question? Is it so far so okay? So how to design, that's all. So that means how do you implement this one? Okay, what you do is at least you have to come up with 1, 2, 3. So 3. This is a flip flop, right? Okay, let me have the same size, for example. So that is one flip flop. I don't know why the size is not the same. I cannot. I cannot. There is a second flip flop, for example, and let's say this is the third flip flop, right? So the first thing is you will have to at least you have to the first thing normally is the clock. You common the clock. So this equation is for this one. This next state circuit. Yeah, the next state circuit. So here you come up with what? You come up with say Q2. Here is Q1. Here is Q0, for example. I do forget it. This line is very bad, right? And then you must have clock. Don't forget about the clock. For each one of this one must have clock. And then the the D, this one is actually D2. This actually go for, this is for the Q2 plus. Q2 plus. Okay, let me remove this one. And then this is Q1 plus, Q0 plus. And in this case, you may have probably 6 possible input. Why? You may have Q2, Q1, Q0, or Q2 bar, Q1 bar, Q0 bar. So these are all D flip-flop. D flip-flop, D flip-flop, and D flip-flop. So this one, not only the output of the D flip-flop or the state of the D flip-flop, but because of the counter, this is also your output. This is a special case for counter. Okay? Sorry for the writing. It looks very, very bad, but that's how I can't. Well, still, this mouse still not nice with me. Again, okay, now we finish with the counter. Again, remember the step is first from the conceptual, you decide the sequence. From the sequence, you come up with the state diagram. And then from the state diagram, you label content of the state diagram with the sequence number. That is actually your encoding that you use. And then you transfer the state diagram into state table. From state table, you get the equation for the next state. And the equation for the next state is basically your next, is the combinational logic of your next state circuit. Yeah? Sequence or next state circuit. or the input for all the flip-flops. Now, the second application of synthesis or design is how to design a sequence detector. This one is a very simple approach in FSM. In the, I think in chapter 11, when we start doing ASM, data path, and then control unit for your milestone 5 and 6. I think I hold on your milestone 5 and 6 for a bit until we get near to that chapter. Now, how to design a sequence detector? Normally, as I mentioned before, you always start with the expected sequence. So, for example, if your sequence is 0, 1, 1, for example. Do we have any chat here? Anyone asking me question? Because I don't see the chat. See? Oh, there is a chat. Sorry about it. Doctor, would it be possible for you to share the QR code? QR code. You're so worried about the things which is not that very important. Okay. Yeah, I will. I will. I will. Okay. How to design a sequence detector? So, what is a sequence detector? The first thing is, for example, if you want to discard sequence 0, 1, 1, 0, let's say, or maybe 0, 1, 1, 0, 1. How many bits? So you start with the sequence. But also, you need to know either you are using milli, right, or more, isn't it? Now, if you use milli, let's see, 0, 1, 1, 0, 1. Now, if this is your sequence, you require how many state? Hmm? If it's milli, 1, 2, 3, 4, 5, straightforward design, you require 5 state. If you use more, you have to go through all the process 0, 1, 1, 0, 1, detect. So you need 6 state. So start with the expected sequence. I mean, start with, for example, this one. Let's say if I do more, if I do more approach. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Right. So that means I will label this one the name as 0, as 1 later on. So let's say this is as 0, as 1, as 2. Now this one you have to know first, milli and more. So I'm doing more. As 0, as 1, as 2, as 3, as 4, as 5. I have to do extra. And we know that 0, 1, 1, 0, 5 bit, obviously we need the output has to be here. So the rest doesn't have output. So what the rest you don't need to show the output. If you want to show all is below is 0. So I think it's better to avoid the messiness. Better just leave it. And then maybe you can say which of this one is the first. So you do reset. That means you always start from this and then you go, what it means by start the expected sequence. From here, I've got problem with the pen. You go from here to here. My pen is not working with me. Okay, here. Okay, you label it as 0. And then from this one, okay, label is 1 from this one. 1 from, let me do this. Okay, so 0, 1, 1, 0, 0, 1, 1, 0, and then last, okay, 1. So this is what you mean by start with the expected sequence. And the last sequence is 1. If you use milli, you stop here and then you return to the 0 with the output 1. I think we will show. And then only as the output at the last here, as the output at the last. Add exit arrow to cover all possible transition. Then, what is the possible transition? Now, let's say if you start from zero, state zero, you have two possibility of input, 0 or 1. So that means what happens if you start from 1? You should not move to another state. So start 1 here. Now, so state 0 settle. Go to state 1. From state 1, if it's 1, go to state 2. What happens if it's 0? If it's 0, you have to go back to itself, right? Because this 0 we need for this one, right? We can use this one as the 0 and we can be 0, 1, 1, 0, 1, right? Settle for the state 1 and go to state 2. State 2, you can either have 1 or 0. But if you have 0, you cannot go to itself, right? Because if you go to itself, you missed out on this one. So in other words, where do you go? I think you can go here, right? Well, because if you go here, if you go back here for 0, your sequence will be 0, 1, 1, 0, 1. As long as you can get that pattern, is okay. So 0, 1, 1, 0, 1, which is this one. So S2 is settled. How about S3? If it's 0, go here. Whatever is 1. If it's 1, what happened? I think if it's 1, you have to go back here, right? Because you cannot back here, you need the first 0. So the first 0 is only coming from here. Therefore, if the from S3, if it's 1, you have to look for 0. So that means you have to go back here. Oh, don't mind about my bad drawing. And you return to S0 so that you can obtain the 0. I mean, you have to reset the whole thing that you've got is useless. You have to restart from the beginning in order to catch the 0, right? So that's settled for S3. And how about if you are in S4? If we want go here, if it's 0, if it's 0, it's okay, right? For 0, you don't have to start from the beginning. You can start from here, right? So you can go from here. You can go here. Because this 0 will be counted. So it'll be 0, 1, 1, 0, 1. Okay? And here, what do we do here? For more simple, once you finish the sequence, you just reset to the beginning. That means from here, you don't ask anymore because if this one, either 1 or 0, make it reset to the beginning because you already have the output. So either you don't put anything on the line. You cannot say 1, you don't put anything on the line. Okay? So this is how you come up with this one. Or alternative, rather than you put 0, 1, 0, 1, let's say if the input is X, the input is X, then in the place of 1, you put X. In the place of 0, you put X bar. X bar. Also can. So that means here in place of the 1 here, you use with the R, for example. I mean, you give the variable. So if you put variable on the transition, what it means, without bar, the variable is considered logic 1. With bar, the variable is considered as logic 0. Okay? So I think the first thing again, remember, do the possible and then only you start figure out the rest. Okay? And it has to be enough. Right? Any question? Right. This is an example. If you run on your, this is an input example. Now, could be, I mean for your test, for example, could also be you are not given the sequence, but rather you are given undo. How do I undo? Annotate. This is the fastest way so far. All right. So you are given. You can also be given the sequence and the input and the output. I mean sample process or sample input output relationship. So from this relationship, Okay. From this relationship, you know the output is triggered when 110 and then 110. So these are the combination. These are the combination and then 110. These are the combination. So that's how. So that is actually also another way for you to know the sequence. Eh? So this is what? This is again more. In the case of more, because your sequence is 3-bit, you require 4. But sometimes it's also possible that you want to keep the output for 2 pulses. For example, zeros, the detect once upon detect 110, you want to keep the output 11 for 2 times. So in that case, you have to extend one more for the other output. One, go one without straight away go one, and then only return. You can do that as well. That's right. I mean the S3 and they add another one S4 with the output also one, but no condition. If you want this one, for example, to be one. Okay. So in this case again, you start with 110. So you start with the sequence and then the output is 000. But it's a bit, it looks messy when you have the zero and the zero. So sometimes you can just show the activate output and the rest is considered zero. Don't care. It's just consider zero. And then from the state here, once you have one, what happens if it's zero? Yeah, you have to wait for one. Therefore, you have to stay in that state. Don't go anywhere. Then use settle. So 0 S0 is settle. Then go to S1. Okay. Go to S1. What happened? Mm, uh, if 1, it go to S2. What if it's 0? So again, you want to, if it's 0, obviously you have to go back because you need to start from 1. So you need this one. So you have to go back to S0 in order to catch this one. Right, you go back. This one. Now this is settled. Then go to S2. S2, if you found another one, that means it can be 1111111. You can take like for example here 1111. This is in this state. It goes here 1 and then stay 1 and stay 1 and stay 1 until you are waiting for 0. So once you see 0, you go to the next step and you find your answer. Okay. Now why do we have 1 here? This is actually your result. Mm, okay. In this case, it's considered overlap. In my example just now, what is the sequence? Probably you can do like this as well. For example, you want to have 110. So rather than going back to S0, you can go back to S1 because this is 110. You still can get that 3 sequence. The one that we have just now is starting from 0. Maybe you can modify into this one. Yeah. If you go straight to S0, actually what happened is that you skip. You missed out. You don't recycle. I mean, you always reset. And that is also depend on the situation. Yeah. Okay. So this is also a pattern. And what if it's 0? 0, you have to go back because you want the 1 start. So this is a this is another approach. Meaning from the last state, you want to consider the last state. I mean, you consider 101. 10. It's a bit strange. Can we consider 110? 10, 1. 110. Yeah. As long as you can go 110, finish complete, you can still come to the output. Well, I think the other one maybe can consider again, the one before, because I assume the last state always start from a restart. Once you reach the output, because my approach just now is more like a vending machine system that you always restart. Once you dispense the money, you restart. But actually, it could also be like like I think the actual vending machine, if you remember, let's say the cost is 15 cents, but you put 20 cents. So after dispatch, the system has to remember the additional 5 cents. So this is a situation whereby you keep you go back not from the beginning, but from where you still have some value. You consider whatever balance. This is like the balance. You consider the balance and then you proceed. Okay. We will do some exercise for this. Um, okay, this is another sequence. I think always go more. So another more. Is it the same as the one before? Before is 110. Now is another one. Oh, this is like if we want to complete the story. That means if we want to do the complete design. So that again, from you have to know what is the sequence. From the sequence, you have to know whether you want to implement using more or melee. And then you come up with the state diagram. So that will be only the design has to come up with the state diagram. And from state diagram, you decide on the symbol. Here you do S0, S1, S2, S3. That means you don't give codes, binary code for the states. Then you decide to use code. So here you use 0, 1, 2, 3. This is actually using binary coding. You can also use 0, 1, 3, 2. That means you use gray code coding. Actually, quite often gray code coding can simplify your function. And here the 0, 1, 1 here is the input here. This is actually this input. Yeah. So 0, 1, 0, 1, 0, 1. So you can use two line. I mean, this is from state 0, state 0 here. If your input 0, remain in that state. If it's 1, go to state 1, which is 0, 1. Okay. And then you can forget about the output first because the output simply depend on the state. And it depends on the present state. Okay, remember present state. So that's why the output is S3. S3 is 1, 1. So as long as you are in the S3, you get the output. So the output you can do last also can. It depends on the present state. And then here, for example, you are now in state 1. If you receive a 0, like 1, yeah. If you receive a 0, you have to go back to 0. That's why your next state is 0, 0. If you receive from 1, if you receive a 1, you go to state 2. And state 2 is defined as 1, 0. That's why you go to 1, 0. It's state 2. And so on. That's how you transfer from state diagram into, this is called state table. Eh? This is called state table, and to be precise, actually, this is state excitation table. If you go back to digital electronics, you have present input, you have next state. Actually, in middle here, you have flip-flop input. And it depends on what type of input you use. If you use D flip-flop, here you have D1, D0. If you have JK flip-flop, J1, K1, J0, K0, and so on. So you need an excitation table. But again, we only use the flip-flop because we want you to be concentrate on the process rather than worrying about the flip-flops. So that's why this Q1 plus is actually representing input for D1. This Q0 plus is actually representing the input for D0. So you can simplify a citation table by doing away with the D flip-flop column. Okay. And then what next? What is this? Save annotation. I see. Let's save annotation. What happened? No, no. Let's go. I don't need to save. Next. Okay. Next, what do? You have the, how many? You have the Q1, Q0, and Z. So your output, if you think of this as your truth table, this is the boundary. These are input. This is your input, and this is your output. Now the state table, because K-map only input output. Therefore, now if you look at the state table as truth table, so the present state and the input are your input, and your next state and the output is considered as the output. Therefore, in your K-map, you have to come up with one K-map for Q1, one K-map for Q0, but for Z, in this case, no need for K-map, right? Because you can know already Z is equal to Q1, Q0. No need to waste time. Okay, that's how. But here it's just showing you, but actually no need to show this. This one to just emphasize that Z does not depend on the X. Doesn't depend on the input because this is more, right? So you come up with this from the K-map, you can come up with the equation. In the design there doesn't have don't care. You use all the state, all the possible. And you implement. This implementation look nice. You turn around, and turn around. So you need two flip-flop. So the first thing you do, two flip-flop. Clock must be there. You can do reset because you want to start from zero. So you can hard reset. This is to ensure your system will always, like, you have one main switch to reset. It will reset 00 as state 00. Okay. And this one again, if you use quarters, this is actually, this part is actually this equation, right? Now, if you look, for example, D1, as I told you, D1 is Q1 plus, Q1, Q0 bar. So this is very, looks nice because it complete the system. However, if you do quarters, don't try to do feedback. You label this one, you label this one, and you label Q1 bar, Q0 bar, and here is just label. Just apply label. Even the X and the X bar also you can use label. So easier for you to troubleshoot, wherever. If you do this one the first time, it's okay. But if it doesn't work, oh, then you start tracing the line and then you got headache. And then you ask your lecturer to trace for you. Sorry, I will not do it. I got headache. It's better you to have the headache. Or not create the headache, use label instead of this fallback wiring. Yeah? Ideally, this is what situation. Ideally, that's the situation. Okay. So that is a sequence detector. I think we are already here, right? No. Wait. We are in page 17 just now, is it? Right? Yeah. So next stage, melee. I need to stop at 12:30. So can I stop here? We can continue next time. Yeah. Anyway, for melee, I just tell you, just one this melee, and the rest I think you can figure out. For melee, again, to detect 110, you have to know how many bits. 3 bits meaning 3 state. And the output is labeled, for melee, the output is labeled during the transition. Therefore, what it means is that the output not only depend on the present state, but also depends on the input, on the external input. And therefore, if you look at if you transfer the state diagram into the state table, what can you see? What can you see is that here 0, 1, 2. Now, if you use binary coding, you need only 3 codes for each state. Yeah, you name the state. You can name 00 for S0, 01 for S1, and 10 for S2. But S3, 11, you define, but it not used. Therefore, you replace that as don't care. Here is obviously don't care because you only have 3 states. So this case, you don't use this state. Yeah, you don't use this state, so you put it as don't care. Right? All right. And then the process is the same. from 0, 0, if x is 0, at 0, 0, it go back to itself. That's why you got 0, 0. And then from 0, 0, if x is 1, it go to S1. Now you have to fill up the Z. Z depends on the present state and the present input. Present, yes, sometimes students confuse with the next state. No. The Z depends on the present state and the input. Therefore, if you look at the Z, now at state 1, 0 here, if it go back to its state, for example, from 1, 0, if your input is 0, your output remain, sorry, the output, sorry, 1, 0 here. If the input is 0, it will go to state 0, right? And the output is triggered. So that's what you have. But if you again from the same state, however, now if your input is 0, sorry, input is 1, your output is 0. So you have 0. So now if you look, state is different by two rows, right? So here they are different here because it depends on the x. Yeah. So that's why you see it depends on the present state and the input. Okay. So the process is the same. You start with the 1, 1, 0. So this is your first step you do, and then you fill up the rest. Yeah, suitable. For example, if it's 0, you have to go up in order to start with 1 because you want the 1. Yeah. Now, melee meaning when you implement melee, but because you have 3 state, you still need 2 flip-flop. Yeah. So you have 2 flip-flop, one for Q1, one for Q0, and let's see, and your circuit, you do the same thing, but now the Z to get the equation also depend on X. So that's why your equation for Z can be Q1 X bar, Q1, Q0 X, and so on. Okay. And then I think they just go for the implementation quickly. Well, it doesn't show you the circuit. Or maybe below here. Doesn't show you the circuit. Okay. You can draw your eye. It's terrible for me to draw. But you can just draw. I mean, how many? You need 2 flip-flop. The input for the first flip-flop is this gate. You need AND gate, another AND gate, OR gate, and then D0 and Z. There is an input. That means, again, if you remember, FSM have 3 block, right? You need the next state block, which from this equation, you need the memory block, which is DD, and you need the output block. So you have 3. This 3 configuration, remember? When we study intro to FSM. So this is what it means. The memory or the states, the next state, and the somewhere in here is they call it present state. This is the present state. In between here, or the output from the state is present state. And when you feed back, that is your next state. Next state is exactly from the equation. So what you get is, what you need to find out is the next state, and this is this part, and this part is the critical part. This one actually, even if you blur, you don't know what to do, this one is standard. The flip-flop is standard. Okay, so I think I stop here because I have Tadarus at 12:30. Now it's
Hello,
12:30.
doctor.
Yes, yes. Who is this?
Doctor, actually, I joined your class a little lately, so can you please upload the QR code once again?
You were so worried about the QR code rather than understanding the material, yeah?
Yeah, doctor, I was
Yeah, yeah,
present.
yeah, yeah. Don't worry, don't worry. I'll give you the QR code. I'll give you the QR code.
Thank
No
you.
mark for QR code anyway. All right.
Okay.
Okay. It's just for my record to know because sometimes the faculty asking me how many students participating today. But actually, the QR code is a bit subjective, right? Actually, how many of you today? Eh? Let's see. Participant 44. Very bad. Our class 65, so we have only 44 participants. I want to check on the QR code. Is it really 44 out of 65 students? Minus young boy, 44 out of 64. All right. So I will stop sharing now. Thank you very much. I will share with you some exercise later on for you to for the enforcement of what you learned today. And Yusril,